Okay, yesterday we were looking at that felt like contrived function. We just had to force it to go through the 0.35. And
So,
we just, the derivative was tangent, so we needed a function.
we were anti-direct.
Yeah, using an integral as an antiderivative. And so this is what we were investigating. And it felt like that doesn't seem fair to do that, but it actually is. It's just not a very useful form, we discovered, unless you've got a calculator, and then it's fine. Remember, we decided that the function would be the integral from 3, because this is what we had. dy dx was equal to tangent x. And we wish to write a function, the function whose derivative is this, through the point 3,5. Remember? That was our objective. So we started at 3 and went to x, so that it would go from 3 to 3 when x was 3, so that we'd get a 0, would be the inverse tangent, not inverse tangent, the integral of tangent. And then we just added 5, and that forced it to go through the 0.35, you recall?
Yes.
And we said, that doesn't seem quite fair. We didn't do anything. And in the old days, they would have said, yeah, but how do we integrate tangent x? Because we haven't got anything, we don't know what that, we can't do anything with that. With the calculator, you can, maybe. We'll discover in a minute. But they did discover eventually by working at it, discovering things, that the antiderivative of that is actually the natural log of the absolute value of the cosine of 3 over the cosine of x plus 5. We'll learn how to do that in the next chapter.
Well, it seems
But-
to have stuff to do with the integral.
We had
X's and 3 and 5.
we had the discussion that both forms are useful and about the same amount of time to plug into a calculator if you wanted to evaluate, say, f of 4, capital F of 4. I should probably call this capital F to be true to what's going on, since this is an antiderivative. Okay. And we decided that would be fine if we just wanted to find a particular value of this function whose derivative is tangent through 3,5. But if you wanted to actually look at a picture of it, that's what exploration 1's about. That's what we're going to try to do. So, you all know how to put an integral in your y equals screen?
Yep.
All right. So see if you can graph our new function in the integral form.
The natural log.
Do it on a standard screen, Zoom standard.
And then
Still going. This is taking a while. This is not-
and it's supposed to go through the 0.35.
Does it take a while? Probably not as long as yours is taking, from the sound of it. Because it's,
Have you tried it yet?
did you do X equals X? Wait, that's derivative. No. It's still low.
I don't think it's
Yeah.
loading. I think you broke it.
What are we graphing?
I
That
think
function.
that what you're expecting to show up is because you have not remembered that you are the master of the calculator, not the slave.
Right.
What is it trying to do? What would be the, if on this, what is it?
trying to count up.
It's trying to find the area under tangent from 3 to -10 first. That's the first thing it's trying to calculate.
3 to negative 10.
Because -10 is the far edge of the thing. Finally quit, finally said yeah.
Full not met.
Said tolerance not met, right?
Yeah.
That's what it means. Eventually it will say that. And that means that there's something you haven't considered.
This go from negative 10 to 3.
Well, just hang on just a minute. What that's asking it to do, the very first, because you've got a screen that goes from -10 to 10. So it's going to start on the very leftmost value. And it's going to put a -10 in where x is there. And what it's trying to do is plot the value of the area under the curve from 3 to -10. It doesn't matter that it's negative. That part isn't the issue.
Oh, there's no value? I mean,
Think about what a tangent curve looks like.
Oh, it's that.
infinity.
Asymptotic, and there are several asymptotes between 3 and -10. And it cannot jump over those. It cannot fill in the gaps and find the area under the curve because there are several branches of it that are not connected. They've got an infinite discontinuity that you can't fix. See what I'm saying? So that's why it's saying I'm working on it, but I can't do this because when I evaluate tangent at -10, I've got several places where the area is leaking out, and I can't figure that because it's leaking there, if you will, near the asymptotes. There's several. It has had a real difficult time doing that.
So if we put in sine, it'll graph it.
Pardon?
If we put in sine, it'll graph it.
Yep. Okay, because there's no leaking, there's no problems with it. Now, take a look at example 1, or exploration 1. It says graph the function, which we tried. It says you will probably wait a long time and see no graph. Then it says break out of the graphing program if necessary. So get out of there. And then it says recall that the graph of the function y equals tangent x has vertical asymptotes. Where do they occur in the interval from -10 to 10? Several places, multiples of pi halves, if you'll recall from your trig experience. Okay, pi halves is only 1.57. So it's going to happen several times before it gets to 10. Y'all following? Okay. Then it says, when attempting to graph the function, which we've got up here, on an interval from -10 to 10, your grapher begins by trying to find f of -10. In other words, from 3 to 10. Explain why this might cause problems. The asymptotes, it can't find the area when it encounters an asymptote. A vertical. Horizontal ones maybe, but not vertical ones. Jump discontinuities we discovered are okay. Remember, we were able to find the area, for example, the graph of int x, if we wanted to go from 0 to 5 of int x. That has a bunch of not really horizontal asymptotes, but places where it's not defined. And all it did was when one step stopped there, the other one started here. And we just drew a line there and said, okay, that's going to be able to be closed up and be a rectangle. We can find that. Remember that? We did it with the absolute value of x over x as well, where we got a graph like this. Absolute value of x over x was 1 out here and -1 here, and we were able to just close that off and find this rectangle and this rectangle, find the area. Can't do that with vertical asymptotes. You got jump discontinuities, okay, as long as they jump at this x value up to this x value, like we have here. As long as they jump that way, it's not a problem. But vertical or infinite discontinuities, it's getting closer and closer and closer and closer to that thing, but there's still a little bit of area all the time. And it can't tally it up. So it's not how to do that. Okay?
Wait, does that mean there's an infinite area there?
Sort of. That's not exactly.
Okay.
You'll discover that in second semester calculus, how to deal with that. It has to do with series, and I don't want to get into it, but it isn't quite that. But it serves our purpose to understand that as that gets closer and closer and closer, it feels like the area that's been established so far is leaking out, and you can't find it definitively. Okay? All right. So now it says, set your viewing window so that your calculator graphs only over the domain of the continuous branch of the tangent function that contains the point 3, tangent 3.
So negative.
Because that's the x value we've got to work with, okay? So consider this. We got to consider the graph of tangent. We got to go back to trigonometry for a little while. And if you'll recall, tangent behaves like this. At pi halves, and negative pi halves, there are asymptotes, vertical ones. Do you agree?
Yes.
Okay. Think about the unit circle. It's not defined right straight up and right straight down because that sine over cosine and cosine is 0 there. That's why it's undefined. Okay. And it goes like this. It goes through the origin, and the regular old tangent curve comes up like this and goes down like this. However, this number right here, this x value, is about 1.57, we'll say. And that's not the x value we're considering. We want it to go through 3,5. So we've got to find the branch of tangent curve that contains the point 3,5. In other words, has a domain with a 3.
The next one over.
Okay, the next one over would be the next asymptote would occur where? 3 pi halves?
Yeah.
3 pi halves, and that number is about, does anybody know? 4.71 is about where that occurs. So between here and here is where our 3 is going to be. And so we put an asymptote here and a branch of the curve here. It goes right through the middle just like the other one does. It's just behaves just like it. Goes up like that, comes down like this. And 3 is at about where's 3?
A bit to
A
the
little bit to the right of this, because this would be pi, no, a little bit to the left of this. 3's right in here somewhere. And so pi is right here, right? Yeah, okay. So this is the branch that we want to use. That means we have to restrict the domain or the x values in our curve, I mean in the calculator, to go from here to here. But you can't actually include here and here. You'll have the same problem. How much in would you like to come so that you can get a pretty good idea of this area from 3 to whatever on this branch? I'll show you a really cool thing about your calculator, and you probably already knew it, I don't know. But leave the y equals screen where it is and go to your window, and for your x min, type in pi halves
minus.
plus 0.01. We want to get in a little bit from it. So when you go to your x min, write in pi halves, type that in exactly, pi divided by 2, and then just go plus 0.01. That's only taking us 100th of a unit in from there. But at least we're not on the asymptote. And what will your y max be?
3 pi halves minus
3 pi halves minus maybe 0.01. That'll just take us barely inside there, like that. Okay, let it scale by 1s or whatever. It doesn't really matter what the scale is. And then graph again and see if you're getting something this time. It may be slow.
Very slow.
Yeah.
I'm still not getting it. Look at that, how we made it. We almost have enough time to.
There we go.
Almost have enough time to bet on which pixel is gonna do that.
Somewhere.
Come on. Oh, here it comes, yeah.
Come on, Bertha. It's like
Okay, if you,
pixel.
what's that?
per pixel.
Yeah. The reason why is because it's got to find the area under the tangent curve at that x value and plot it, and then go find the area under the tangent curve using a Riemann sum every time and plotting that value. And
This
that's
is like
it's an awful lot of work for it to do, for that little processor that's in here to do it, but it does it a lot faster than we could. It does it for every pixel rectangle, every pixel that's available to it in this window. And that's the reason why it's taking so long. If you don't want to wait. If you don't want to wait for it, then just hit the on key. That will abort it. And then let's talk about some ways that we can get it to graph faster, just so that you know, understand your calculator. On page 298 at the bottom, he talks about this. He says, you probably notice your graph moves slowly when graphing nins. This is because it must compute each value as a limit of sums. Incredibly slow work even for a microprocessor, and here are some ways to speed up the process. There's 3 different ways. I like number 2 the best. It says, number 1 says change the tolerance on your grapher. You can do that, but it requires more typing in the y equals screen. I don't like doing that. Next one is to change the x resolution. Remember in algebra 2 when I said never mess with the resolution?
Yeah.
Okay, well now we're going to mess with it. So I want you to go back to the window, and I want you to go down to the resolution and maybe change it to 2. When you change it to 2, it will go to every other pixel, and we'll only have to do half the calculations. If you change it to 5, it will do every 5th pixel. But you sacrifice smoothness of curve. So if we were to just go to 2, that should cut the time in half.
Well,
Go
it's
X resolution
so
2. And it should come through quite a bit faster if you do that.
Wait.
It's cruising compared to before. It's still not cruising, is it?
The extra
No.
thing.
What's that?
The extra.
Oh, wow. Yeah, extra. Do a 5.
That's
Do
a
a
5 now.
And in the branch that we're looking at, we get a fairly symmetric looking little curve, right?
Oh, this is still taking a while.
What is
It's
it?
faster. It's
Because of the
fast.
top, anyway.
Do the 5, guys.
Okay, so here's the moral of this story. The moral of this exploration is you better be careful if what you're trying to integrate has asymptotes.
Mine never finishes.
Hey, what's that?
It never finishes.
I know, it's because it perceives it as being vertical at that point, I think.
Oh,
That's the problem.
I guess.
Mine never did come through, and it just dawned on me. I wasn't in radian mode because I switch back and forth on my calculator with what I'm teaching as I go through the day. So mine was all,
See how I just
yeah, here
did
comes
7.
mine. Okay.
You just what?
I just did 7.
I'm gonna do 50.
Okay, so describe the graph of F. Oh, mine finished. Did yours finish? Yep, finally got yours.
It wasn't much faster than 5.
It looks like a really, really shallow, wide bowl, doesn't it? That would be a good enough description. They just want you to be able to, they just want, at the very, very end, it says describe F. It just want to make sure that you actually got it graphed and did everything we're supposed to, so you can
Mine looks like a dog.
get an answer to it.
How can you even do 50? What do you mean?
I can't do 50.
Maybe I couldn't either. No, it went down to 5 something.
Oh, yeah. Yeah, 5.
Can you describe why your graph turned out that way, do you think? Remember, what's being plotted here are areas. Areas from 3 to here for very, very first one, if you will. I'm going to have to draw my .01 in
That's what I
like this.
know.
So what it's doing in the very, very first plot is it's plotting this area of this rectangle right here.
So that's
So it's pretty good size.
So it's
And then it plots this one. And if you increment it or you change your resolution to 2, then it's only doing every other one. So then it plots this one, and then it plots this one,
oh my
and
gosh.
then this one. And it's plotting the area so far. Okay, and so when it gets right down here, the area is still is being contributed to it, but it's at a very, very slow rate. That's the reason why it flattens out near the
So
bottom.
why is it negative to the left of 3?
Because it's integrating from this
it's
3 right
negative
here
3, okay.
left, which turns out to be positive.
Oh, okay.
You follow?
Yeah.
Kind of.
Why did
So this isn't completely and truly 100% symmetric, because right here at pi, which is very, very close to 3, it now goes from here to here and moves up. It's not, that thing isn't 100% symmetric. But anyway, I'm just trying to show you that you get pretty large areas at first and they diminish quickly. So they're coming down, flattening. And then they gather, then it gathers more area pretty fast. And that's the reason why they have that shape. Okay, so you now know how to get a graph. If it's really slow, abort it, go change the resolution to something to a higher number. Every time you go up a number, that's it'll do it if it go up to 3, it'll only do it every third one, but it'll graph 3 times faster, so. Just a thought there.
Could you do like a decimal?
I don't know, you try it.
I'll try it.
Try 1.5,
Wait,
No.
1.5?
doesn't want to do that?
No.
I think it's because it's counting discrete pixels. You know, 1, 2, 3, 4, 5, you can't do it, half a pixel doesn't work for it.
I can change that.
Okay, so
Oh, you can change
we kind of did things out of order. I talked to you about the resolution thing. I've already talked to you about exploration too, but it doesn't hurt to revisit this. I was talking mostly to Axel when he asked me the question. He doesn't remember it, but he will, so they bring it up. And what the thing was is that if you are doing the derivative of an integral, like the first part, that's has to do with this. So I can't leave because Savannah won't be able to see, so I'm going to erase this. When we were trying to take the derivative of an integral like this, and we started at some constant to x of some function, it didn't matter where we started. It does not what?
The d over dx, that's just another way to write derivative, right?
Yes.
Okay.
This is the derivative of this stuff with respect to x. That's what it's saying, okay? All right. And we said that if you're taking the derivative of the integral, that it doesn't really matter where you start, because what this question is asking is how quickly is the area changing here, not where we started. Does that make sense to you? How fast is the area changing? That's what it's saying. The rate at which the area is changing here. So it doesn't matter where we start. However, it's a big deal if we're trying to do this. If we're trying to actually find the area under the curve, it matters a great deal where we start. This is the second version, or the second part of the fundamental theorem, which says that you take f of b, the antiderivative, minus f of a. So it's very important here where you start, but it isn't here. Because this is a rate at which area is changing, so the start point is irrelevant. That's what exploration 2 is all about. We don't need to go through that, but I'm just saying that's what they're trying to discuss with you and try to drive home to you. Okay, fundamental theorem part 2. This is part 2, according to this book. In every other book I've ever seen in my life, that's part 1. But anyway, this is part 2 for our book and our authors. And you've already had some experience with that, so I'm not going to spend a lot of time developing that for you again. It's on that paper that I gave you. Now let's take a look at example 5. And now we're actually going to evaluate an integral by actually anti-deriving, not by alluding to any geometry or making our calculator find it. We're going to do it by hand, anti-derive. It's not very hard. So what we wish to do is to do this one by hand, the integral from -1 to 3 of x cubed plus 1. Okay, so we have to find the antiderivative of that function and evaluate it at 3 and -1 and subtract them. Do you understand the process? Do you understand what we have to do?
Yes.
Okay, the antiderivative of that particular polynomial is what? What will the power have to be?
1/4.
1/4, not 1/4.
3/4.
Four.
So
And you're gonna need a
1/4.
1/4 out here, so that if you derive it, you get x cubed. Do you understand that? Okay, and what's the antiderivative of 1? X. And we're going, this is the notation we use, we're gonna evaluate that from -1 to 3. That's just to remind us where things are and what order they come in. Now that we've got the antiderivative, this just reminds us over here, it's just notation. So it's gonna be 1/4 of 3 to the 4th plus 3 minus 1/4 of -1 to the 4th plus -1. We have to figure that out. Because this right here is capital F of 3, this is capital F of -1. And so we get 81/4 plus 12/4, if you're okay with what I'm doing. You okay?
Yes.
I'll come back and grab that in a minute, but I'm just getting common denominators as I see them. This is going to be 1 times a 4, so it'll be a 4th minus 4/4. We good? Okay, 81 minus 12 is? Oh, plus 12, sorry.
93/4.
What is it?
93/4.
93/4 minus
Positive
positive
3/4.
3/4. 96/4, which is
24.
24. So that's how you would do them by hand. You have to actually antiderive it. If it's a polynomial, it's not a very difficult thing. And then you evaluate that at the top interval, or the top limit of integration minus the bottom limit of integration, plug into that antiderivative, work out the details. Okay, not too bad. Okay, take a look at example 6. It says, find the area of the region between the curve y equals 4 minus x squared and on the interval from 0 to 3, and find that trapped in between the x-axis. If you actually graph that, you get the graph to the left there. And when it says, and I want you to pay attention to this because I just glossed right over it, which your eyeballs probably will too, unless I teach you, hopefully you'll be able to catch it. It says find the area of the region. It does not say find the integral. It says find the area. Which means that you can do it one of two ways. We're going to talk, I've already talked to you about the other way. But this is one way to do this. We can integrate from 0 to 2, and then integrate from 2 to 3, and change the sign on the 2 to 3 region. Right? Because if you integrate the area from 2 to 3, it's going to give you a negative number.
Yeah. So is when you integrate something, does it find the area with signs?
Yes.
Okay. But if you want the area, then you just like absolute value.
Yeah, you have to find your negative areas and make them positive. Okay?
Oh, so it's just absolute value.
It will be in just a minute. That's another way to do it. But for this particular example, for right now, we're not going to do it that way. We're going to jump. We're not jumping to there yet. We will. That's an excellent observation.
Is that the second way you think?
Yes. Yes. This way, however, I'm observing the graph and saying, okay, I'm going to integrate from 0 to 2. That'll automatically be positive. Then I'm going to integrate from 2 to 3, expecting a negative. I will make it positive and add it to my first one. And that will be paintable space or area. Okay? Just to show you, there's a couple ways to handle this. And sometimes this is preferable. Depends on your integral. Most of the time, the absolute value is best, especially if you're allowed to use your calculator. They don't want to see it analytically. If they want to see it analytically, this may be your best bet. Because dealing with an absolute value as part of your function can be hard, really difficult if you have to do it by hand. So this method has its uses if it says you're going to get full points only if you show analytically what's going on. Okay. So the first thing you might want to do is graph 4 minus x squared when you're trying to integrate from 0 to 3 and see if it's all positive, all negative, or there's pieces. And we can see that there are pieces. So this is our ultimate goal, is to integrate from 0 to 3 of 4 minus x squared dx, and we wish to find area. That's, well, maybe I should write that. This is the integral. But we want to find area, which means we are going to have to integrate from 0 to 2 where it crosses the x-axis. And add on to, which really means subtract the negative area from 2 to 3. We expect this to be negative.
Yes.
So if I put a negative here, it will turn this positive. You see what I mean?
Yeah.
Or we could do this. That would be fine to add that on, if when you get an answer for this, you don't forget to do that to it. You know what I mean? One way or another, you have to account for it. And we can do it with a sign, or we can do it with an absolute value. What's your preference?
So absolute value.
Absolute value. Okay, then we'll integrate both of these, and remember, this one's got to have a sign change.
Okay.
Basically, what it means is, do both of these, and whatever you get, make them positive. Because space is positive, okay? All right, so what's the antiderivative of this?
1/3 x to the third.
What's the first one?
4x.
4x.
1/3 x cubed.
You agree?
Yep.
And I will first evaluate that from 0 to 2. We plug a 2 in there, we're going to get 4 times 2. I'm just going to do some of the arithmetic in my head because I'm sure you can too. 4 times 2 is 8. That's going to be 8/3, right?
Yep.
And when I plug a 0 in here and here, I get nothing. So that's going to be -0. But people, this is one of the biggest mistakes calculus students make. When they see a 0 there, they have done it so many times and realize that when they plug 0 in, they get 0. They think, oh, when that's 0, I only have to evaluate that one. Sometimes, like when you involve cosine, you are going to get a value out when it's 0. So don't ever forget to consider 0. Though most of the time it will return a 0, don't assume that it will all the time. Make sure you always consider it, okay? So in this case, it turns out to be 0. So I'm going to end up with 24/3 minus 18/3 is 16/3 for that one. You agree?
I guess, yeah. Yeah, I just.
24 minus 8, 16?
Yeah,
Okay.
I just didn't do that in my head.
Okay, are we good? Okay, so this one is the exact same antiderivative, 4x minus 1/3 x cubed, evaluated from 2 to 3. Now we are going to have to consider them both. If I plug if I plug a 3 in there, I'm going to get 4 times 3 is 12. 27/3 is 9. Did you catch that?
Yes.
We good? Okay, so that's the first plug-in. I'll do that in just a minute. If I plug a 2 in there, I'm going to get the same thing I got over here, which is 8 minus 8/3. We already know that that's 16/3. So this is going to be 3 minus 16/3. That's 9/3 minus 16/3 is 7/3, negative. So we absolute value that. Add it to 16/3 and we get
23/3.
23/3 altogether. So the area is equal to 23/3 altogether because we have the absolute value of the negative part. We good?
Yep.
All right, now if you're allowed to use your calculator so that it handles the absolute values with no trouble, then you would do it like example 7, one like example 7. This says, find the area of the region between the curve y equals x cosine 2x and the x-axis over the interval from -3 to 3. And they show you 2 graphs there with the area painted in. Can you see that if we just found the integral, it would be 0?
Yep.
Every single piece that's above the x-axis is reflected below the x-axis on the other side of x. And so you would get 0 if you just integrated that. But if you want to find the area, what it does, well, you use the absolute value, it flips all those negative areas to positives. Now you've got a positive region. And your calculator can find it. And it doesn't mind using the absolute value. If you try to integrate something like this by hand, I say, good luck. It's hard. It would be easier to go back to this, actually. It's hard to deal with. Your calculator has no trouble. So y equals, so everybody see if you can punch this in and evaluate from -3 to 3. Make sure you put the absolute value in where it goes.
That's what I got.
Did you get what they got?
Well, we weren't supposed to put this in our y equals screen.
No.
No. Listen, I did, just so you know, I did exactly the same thing, and then I realized,
That's
oh,
what I
I
did.
probably evaluated it. I'm trying to get a number. Well,
Get a
back
number
on.
on the graph.
Yeah, should be an alternate.
You got it in y equals screen, then like.
What were you planning on doing, Sam?
You would have to do like remon or something on it, wouldn't you?
Oh, wouldn't you just like
You just plug in the
Yeah,
point.
today
You can actually ask it for an integral on the screen. Did you know that?
It'll just give you a
Yeah,
dot.
but I'm not gonna.
No, it
Oh,
won't. It'll
that.
shade in the area. And then tell you what it is.
Wait,
You guys wanna learn how to do that?
Is it what
Yes.
yes. Is it
Okay, so
what
go to y equals, and you type in the same thing, right?
But it
I got it.
takes 10 hours to graph.
Insert.
It's probably calculating integral.
Lower limit.
We can enter.
I would go change your X res.
We want absolute value, right?
Oh, well, that's cool. For the X res to
Calculate integral.
How'd you say that?
Because his is legit.
This is
It's not as nice as that one. Second, wait, do we do Zoom standard instead of
Sam.
You could if you want.
Okay.
And maybe put the resolution at 5.
Yeah, that's what I did. And it's still. And then when I have, then you graph the thing.
What's your window?
-33 back to why you make it
I'm not seeing anything.
Oh,
No, I
she's
just
coming
started.
in.
There's one.
I see a dot.
Itty bitty dot.
Who's this?
This is a really bad one to show you
I see
on.
a dot.
This is a really bad one to show you on. Abort this thing, and I'll show you how you, if you want to take it. This one is not good.
Let's do like.
Go back to y equals and integrate, say, x squared from 0 to 3.
Sam.
Root x?
Yeah.
Okay, so root x, fine, that's fine. So try to, in your y equals screen, go,
From 0 to 3, right?
math 9.
So you're 33, right?
You just standard screen.
go
0 to. What should we do? 10? 0 to 3.
Calculate.
Square root of x,
Well, it's 7, isn't it?
What are we doing?
comma,
0
X.
to.
comma. If we go from, let's say 1 to 5,
Oh, 1 to 5. I didn't really tell me.
I know, I'm gonna go 1 to 5,
Okay, I'll go
On mine.
10.
and I'm gonna set my window to standard.
Whoa, that graph's so quick.
Here's 2x squared.
It filled it quick.
How's your square?
Wait,
Oh, you know what, I'm doing this wrong. Go back, stop, abort that, and go to y equals, and don't put f int. Just put the function, just put root x, that's all, just root x. And none of the other junk that goes with it, just root x, graph that, you see that graph,
That was
and
fast.
then
Oh,
you
really?
can
That
go
was so fast.
second, calc, and then number 7.
Was it? Watch how fast it shades it.
And it will say lower limit, I'm gonna say 1, upper limit, 5, go, and it will shade it and tell you what the area is.
Whoa.
So you're sure you got what you want. But the thing is, you put the actual function that you want to integrate. You don't ask it to integrate it. You don't ask it to integrate it. You just put this function in, whatever it is. In our case, x cosine 2x. Just put that in and ask it.
This is faster than Mint, isn't it?
Yeah, I mean, you still have to do the same amount of typing.
Can we do
And
it
you can
again?
and you can analyze several values at one time instead of just the one you're looking for. If you're only looking for one, home screen, and this is about 6.1, that doesn't yet. So,
That's so fast.
Savannah,
6.78.
you put just the function in like this, root x, and then you graph it. And you can, when you go like this, you go second calc, and then go number 7, in case you were not listening or didn't follow what was going on. And then it will ask you for a lower limit. If I change the limits on this now to maybe 2 to 8, like that, it'll shade it in and tell me what it is at the bottom of the screen. I hope you can follow that. If not, talk to me later. Okay.
So if you wanted to find the area, could you put a function in absolute value in the y equals screen and then find the integral of that?
Ask it the integral from here to here, check. Yes. I just wouldn't try to anti-derive by hand something in absolute value. You can't, it's hard. It's not worth the effort when this thing can do it.
I really don't want.
Okay, so we all understand now that you can actually see a picture of the shading and actually find the value in the screen, in the y equals screen, but you don't put the integral in the screen, you just put the function. Y'all clear?
I got the other one done. I'm working on the other one right now.
Cool, all right.
Nice. Good job.
Okay, we have only one more thing to discuss, and this is conceptual, and they love questions like this on tests that count. They want to make sure you understand the calculus. So I need you to look with me at example 8 and really try to think with me. And then when I'm done with that, we'll be done. So watch what's going on. Please don't turn the page. We're not going to look at the solution. It says, the graph of a continuous function f with domain 0 to 8 is shown in this figure to the left. By the way, Savannah, we're on page 301 at the bottom. It says, let h be the function defined by the integral. Now remember, h is a function defined by the integral of 1 to x of f of t to t. Now let's remind ourselves what we're looking at here. The graph of a continuous function f from 0 to 8 is shown. So h is a function that is the integral of what we're looking at here. From 1 to some value of x between 0 and 8. So it's the integral from 1 on. So what do you think h of 1 is?
0.
0. It's correct, because what they ask you to do is to replace x with 1, and you have the integral from 1 to 1, which we know is 0. Are you all clear? Okay, next one. Is h of 0 positive or negative?
Would it be negative because you have to
flop the thing and have become a negative function.
Okay, the area itself from 0 to 1 is positive, but you're integrating from 1 to 0, which makes it negative, because you're integrating backwards. Now, had the actual area underneath that curve from 0 to 1 been negative, your answer would have been positive.
Oh my gosh.
Yeah, you've got to pay attention to where you're starting, and we're starting at 1. And if you want to integrate from 1 to 0, which is what they asked us to do in B part, you're integrating backwards, which means whatever the area had, whatever the sign on the area is now the opposite of it.
Is this the graph of the integral or the graph?
No, that's
of
the
what
graph of
you're
the function.
integrating?
That's the graph of the function that we're trying to talk about areas under.
Oh.
From 1 to something.
For example.
So that is h of x.
H of x is the area under the curve. From 1 to wherever we choose to go to.
Okay.
And if we're integrating from 1 to 0, which is what they require us to do in B part by replacing x with 0,
So the graph.
you're integrating backwards. So if you notice that the area is actually a positive area there, a positive number, you're gonna have to make it negative because you're integrating backwards. With your rectangles all have negative widths.
Okay.
Okay, you follow that?
Yeah.
C part, find the value of x for which h of x is a maximum. Pay attention, people.
Sorry.
Find the value of x for which the area under the curve is what you're saying here. That's what h is. Find the value of x for which h of x is biggest.
Would it be 3? Because when you go past that, it gets negative,
Yeah.
so it takes away.
You think so? Do you think he's right? Did you understand the argument?
Would it be 3? Wait. Because if you go to 8, then you've got
Yeah, you've got all the
the
negative.
positive areas, the positive integrals, but then all that negative stuff.
Okay, so where does it have the greatest value? From 1 to what gives you the greatest value?
3, because everything's
Right,
before.
right in.
1 or 4.
4, because
Then you
yeah.
include that
Right.
little bit.
Right.
3 is like.
You've added positive area from 1, you add positive area until you get to 4, and that's what you meant.
Yeah.
You still saw that 3 sitting there, right?
3 was labeled.
Because the reason why I had to really clarify what you were saying is because 3 is also at maximum, and I thought maybe you were considering that. No? Okay.
I was.
You were?
Yeah.
Okay, we're adding area, positive area, from starting at 1, we're adding area positively, more positive, more area, more area, until we get to 4, and then we start to add negative area, we start to detract from that. So the maximum is hitting at 4,
Maximum area.
which is what H is. Y'all understand this?
Yes.
Okay, all right, look at the D part. Find the value of X for which H is a minimum.
0 to 1.
8.
Remember your number line, the farther left you go, the smaller the number. So, where is its minimum? I heard the correct answer, but I didn't hear it from everyone. It is at 8, because by the time you arrive at 8, you have now subtracted as much area as you're going to. You've gotten a total negative space. So the positive number that was from 1 to 4, and the negative number from 4 to 8, when you combine those together, you get the smallest number after you've added the most negative area. Does that make sense?
Yeah.
Okay, next one. Find the x coordinates of all the points of inflection of H. What? Find the x coordinates of all the points of inflection of H. Remember what H is?
3.
H is area under the curve.
Is it the maxes and mins for this?
If you think that's the case, I need an argument. I need you to convince me.
Because one is
This-
concave up and concave down, that's what it changes.
So H of
H
X
is what we're talking about here, not the
H
function you're
X
looking at.
is
Which is
the
the
integral.
Hang on a minute, go ahead.
H of X is the integral, so it's the antiderivative of this, right?
Okay, yep.
And then the antiderivative has points of inflection where its second derivative hits 0, and its second derivative hits 0, where its first derivative, this, has negative.
Maxes. So 3 and 6.
That's a reasonable argument. Did you all follow what he said?
3, 6, and 1. I mean 1, 3, and 6. 3, 6, and 1. Does it matter? Not really. That's just
Okay, did you understand what he said, going back and forth between first and second and integrals and antiderivatives and all that stuff? Did you follow that?
Surprising.
Did you ladies follow that? Tell us again, Connor. Go slow. Take pauses.
So this graph is like f of x, and then h of x
Yes,
is
yes.
its
Doc,
integral
okay. This graph is f of x, which is the
function we're integrating. Second or first derivative.
Of-
H.
h. This is the first derivative of h, which is what we're looking at. From the fundamental theorem, that's what you said. I
That's what she
promise.
said.
That's what I heard.
I thought I said h was the first derivative of this.
No,
No.
h. That is not what you
Wait.
said. You said it right.
You said it right.
Oh, no.
Think about it. If you were to derive h, wouldn't you get f? Because isn't that the fundamental theorem of calculus? Yeah?
Yeah.
So we are looking at the derivative of h.
Yeah.
Okay?
So we're
So where will h have inflection points? Continue.
I don't know anymore.
I got
Okay, all right, Axel will try it. Go slow, pause between concepts so we can get it.
So since this is the first derivative of it,
Mhm.
and we're the inflection points of h, you have to look for where the second derivative is 0. And so since this is the first derivative, the second derivative is 0 at the max and mins of the first derivative. So it'd
Because
be
that's where the
1.
slopes of the second derivative will be 0, right?
Yes.
So if this is the derivative of h, then inflection points on h will occur at maxes and mins. But yes, you have to establish the fact that you are looking at the derivative of h, which is the fundamental theorem we've been discussing.
That's
Turn a page and see if we are right.
yes.
A was 0,
Yes.
B was negative, C was at 4. Isn't that what they decided? F of 4 is the maximum, and we decided the other one was at 8. Is that what they decided?
Yeah.
Yep.
Thus f of 8 is a minimum, and then we go look at the inflection points 1, 3, and 6. Well done, everybody. That's pretty good.
If only I could actually do this.
You can if you get enough experience with it. You'll get it. Okay, so there's the exercises. You're done with 4 you get tomorrow to work on it, and this entire 3-day weekend that you get to work on it.
I actually get it.
We will begin the quiz review and the test reviews early next week, and hopefully get it all done by, that's my goal, okay? All right, I hope that was understandable, even though you didn't get to see much.
And yeah, was it?